Hello and welcome to Physics 1401, College Physics 1. Today I'm going to talk about work and energy. That is chapter 6 in your book called Conservation of Energy. Now, energy is one of those topics where we don't have really a clear definition. Or I should say, we have a clear definition for work, but not for energy. We understand energy by learning how to use, the mathematics of it. When you learn how to use energy, when you solve problems using the energy method, you understand what energy is, For now, it is just something that is conserved. Like we have conserved quantities in physics. Mass, for instance, is a conserved quantity. Energy will also be a conserved quantity. So I'm not going to give you a very good definition because I don't know any. There's none. But for work, there is a good definition, and all you need is a force on an object, and the object has to move from point A to point B. There has to be a displacement, and this force will do work in that direction. When the object moves from one point to another, the force will be considered as doing work, and we have a good, clear, well-defined work formula. So let's start there. Let's start with the definition for work. There has to be an object, and there has to be a force acting on the object. Let's start with the easiest, a horizontal force, F. This is an object with mass m. The mass doesn't really matter for now, but we have this horizontal surface that the object is moving, and then maybe it ends up here at a later time, And time doesn't really matter. This could be slow or fast. We don't worry about that, We're looking at this problem from a different perspective, not from the kinematics perspective, but from force and distance perspective. So let's call this a displacement equal to d, right? You can call anything you like. Now, of course, these are vectors. Force is a vector. Displacement is also a vector. Let me use green. So basically, I'm talking about literally a vector that starts from where the object is and points to where the object will be. That's the vector d. Now I can put an arrow on top. Like I could put an arrow on top of f as well. These two are vectors. Now, the definition has to depend on the force and the distance traveled. You can push an object 1 meter, or you can move it 2 meters or 3 meters. If you increase the distance, you're doing more work. So you expect work to be directly proportional to the distance traveled. Well, if your friend is helping you to push the object, let's say you're pushing a refrigerator and it's too heavy, so you call your friend for help, then maybe you're doubling F, right? Still pushing a distance d, but with a greater force. A greater force means more work. So the work has to be also proportional to the force. Now, before I give you the formula, let's think about the general case. This was specific, right? The force was horizontal. The motion is also horizontal. Now, what if the force and motion were horizontal but pointing at different directions? Sometimes it happens, right? Or let's say you're pushing from this direction and your friend is pushing in the other direction, So is your friend helping you? Not really, right? But he's still doing some work. So that work he does and the work you do will be like competing, right? In competition. So mathematically, you could call them positive and negative. So think about these possibilities. And sometimes there may be a force present, but the force doesn't really do anything. it doesn't help you, or it doesn't oppose you either. Suppose you're pushing an object horizontally. Think about gravity, for instance. Gravity acts downward. That's gravity, mg. All right? Now, since the surface you're pushing the object is horizontal, gravity is not really helping you. It would if you were going downhill, or gravity would oppose you if you're pushing it up an incline, right? But here's, it's not doing anything. So sometimes forces don't do any work at all. So it depends on how you apply the force. Okay, so if the force is applied along the direction of motion, that's when you get most of it. Most work is done when you push it in parallel with the displacement vector. And it's the worst if you're pushing it the other way, like your friend who was, pushing it the other way. So that could be negative, all right? So the work can be positive or negative, or it could be zero, as in the case of mg. It depends on the direction. So to arrive at a general formula, we have to consider also the angle between F and D. In general, this could be your force, and this could be your displacement vector. Maybe you're pulling the object, but you're holding, you attach a string to the object, right? So here's you. You're walking, and you're holding, you're pulling the object with a string. So the force you apply is actually at an angle, obviously. The tension force in the rope, right? But there's an angle here. So this angle here, theta, will be also relevant. In the case of mg, for instance, for gravity, not always, but for this problem that I'm talking about, theta is 90 degrees. 90 or 270, depending on how you measure it, but it's perpendicular to the direction of motion. In the case when your friend was pushing it against, okay, let's say this is your little brother pushing it the other way around, F prime, okay? So what's the angle in this case? F prime would be pointing this way, and the angle would be 180. So if theta is 0, and that's the case for you here, you get maximum force. For theta 180, it becomes a negative force, right? And for 90, it is 0. All right, well that describes the cosine, because cosine 0 is 1, cosine 180 is negative 1, and what? Cosine 90 degrees is 0. Okay, so I'm going to define work for this problem as, remember, it's proportional to D and proportional to F, so I'm just going to multiply F and D, or in other words, the formula is in linear with F and D. It depends on D only, not D squared, for instance. That's what I mean by linear. But I also include cosine theta. Okay, cosine theta. Now, in some cases, you may prefer to write this as F parallel. Those two lines symbolize parallel, a parallel force, parallel to D. So F parallel times D, if you write it like this, then cosine theta is hidden there, because F times cosine theta is nothing but the projection of, let's say we're talking about T here, the projection of T in the horizontal direction is right there. And this is the angle theta. So this side divided by hypotenuse is cosine by definition, right? Adjacent over hypotenuse. That's why F cosine theta is F parallel. All right, so you may see both expressions. This is just a parallel symbol. Actually, there's another way to do it. Also, let's say, since you know vectors and you know unit vectors, you know, and there is this thing called the dot product. Dot product of two vectors, or scalar product. Scalar product. You take the vector f and put a dot in between f and d. Okay? So you exaggerate that dot a little bit. But the scalar means the answer is just a number. Just a number without direction. It's not a vector. Okay? The answer is the dot product of two vectors is always a number. Now there's also a vector product, which we'll see it later in this course. There's also a cross product or vector product. The other name is cross product. Like two vectors, A cross B. The answer will be a vector also, the third vector. Also a vector, and this vector will be perpendicular to both A and B. So call this C, for instance. C will be perpendicular to A, and C will also be perpendicular to B. Okay, more on this vector product later in this course, but just keep in mind there are two ways of multiplying two vectors. One of them give you a scalar. Scalar means just a number without direction. Another way of multiplying them, which is called the cross product or a vector product, gives you a vector. All right, but our case is work, and work now is just f dot d. So work is a scalar. Okay, if you put that dot here, don't forget the arrows either. So that means that's a compact mathematical form. You can just write it as FD cosine theta without problem, okay? So that is the definition of work. F is measured in newtons, and D is in meters. These are the standard units, okay? So Newton meter is the unit for work. But we don't call it Newton meter. There's another name for it. So unit for work in the SI, Standard International Unit System, is joules. Okay, joules, named after the French scientist. Joule is also the unit for energy, which we will see in a little bit. Okay, so work and energy, dimension-wise, are the same. They have the same units. So 1 joule, or J for short, is equal to 1 Newton meter, or if you prefer to write newtons as kilogram meters per second square, remember from Newton's second law, F equals ma, right? So kilograms meters per second square is 1 Newton, and you multiply it by another meter, so this becomes kilogram meters squared per second square. Okay, so the dimension of energy is mass m, and velocity squared, or you can call it L squared over t squared. That is the dimension. Remember, when I say dimensional analysis, I'm talking about this kind of analysis. Dimension of energy and work. Okay? So, example. Let's say you have your truck here, and you're loading your truck with some heavy equipment or your furniture. Okay, but it's too heavy, you can't just lift it. You want to do things easier, so you put a piece of wood here, a plank, a platform. Okay, so there's that angle here, theta. It can be as long as you like, longer the better, right? So you can put your object here. Okay, are we recording, by the way? Let me double check. Recording, great. So this is your heavy object that you want to push. So when you push it, let's say the force you exert is parallel to the incline, but it's not horizontal. Horizontal would be the floor, right, the ground level. But this is your force you exert, and the distance of the plank is d. Okay. What else? The height of the truck bed. This is h. Okay, so find the work. You do. Find work done. The fridge is of mass m. Find the work done by u, which is F. But in this case we have to consider gravity as well. Work done by gravity. Actually, let's think about all the forces present. We have F pushing it uphill. We have mg, weight, downward. What else do we have? We have the normal force that this inclined plane exerts on the object. That is the normal force, N or Fn. And the angle between mg and n from this side is also equal to theta. This is also equal to theta. Okay, so let that be part C. What is the work done by the normal force? All right. And our formula is, in general, F parallel times displacement. Now, yeah, this force is already parallel to the displacement. So the work done by F, right, the work done by F will be equal to F times D. Okay, it's not F equals to FD. Work done by F. Let's write properly. WF, okay, that means work done by U is equal to F times D. Okay, this was easy. What about work done by gravity? Now this is where you have to be careful, because you need the component of the weight along displacement. In other words, mg parallel. But mg is not parallel, right? mg makes an angle with the vertical here. So mg has two components. So let me try to replicate it here. mg is downward. But mg will have components. If you box it, like we always do, this component is what I'm interested in. The other one will help me find the normal force. So this part is mg cosine theta. This is theta here. And this one is mg sine theta. Okay. Now please do not confuse this theta with the theta in the formula I was showing you earlier. Okay. This theta had to do with the angle between the force applied and the displacement. Okay, now in this context I already used the theta for the inclination here. So when I consider, for instance, the angle between mg sine theta, the component of the the weight and the displacement, it is actually 180 degrees. So mg sine theta points this way, but the displacement points in the other direction. So the angle between the two is 180, and cosine 180 is -1. All right, so the work done by gravity, let's call it WG, right? W is not weight, W is work. So WG means work done by gravity. First of all, it's going to be negative because of this cosine 180. Negative mg sine theta times d. All right. What about the normal force? What is the angle between the normal force and the displacement? It's 90 degrees by definition. Normal means 90 degrees. Therefore, the work done by the normal force has that cosine 90 in it. Therefore, 0. Okay, perpendicular forces do not do any work. Now, okay, we have found those three, but let's think about this now. We used an inclined board plane of arbitrary length d, and I remember saying the longer the better, right? Now, why would it help us? Why would it help us to use a longer board instead of a shorter? Why would it be easier? So let's try to prove that. Okay, so let's assume that we're doing this with a constant speed. Okay, we're not accelerating. If we're not accelerating, then the net force along the incline has to be 0 because there's no acceleration, right? So if no acceleration, the net force is 0. That means that F, the force that we push the object with, let's call this the positive direction here, positive F, X if you like, that's F, but mg sine theta is in the opposite direction, therefore negative. So F minus mg sine theta, that is the net force, and it's equal to 0. Okay, which makes F equals mg sine theta. Now, what is sine theta anyways? Look at the picture here. We have a right triangle. Use the definition of sine. Sine is side opposite over hypotenuse. That is h over d. Now, the work done by gravity is mg sine theta d. So sine theta appears there. And also in part A, the work done by me is F times d, but F is mg sine theta also. So sine theta appears in both parts A and B. So in part A, then, since F is equal to mg sine theta, the work done by that force is equal to mg sine theta times d, right? That's what we found. So why don't we plug sine theta in there? So you will have mg times sine theta, which is h over d times d. So what happens? D goes away. Okay, so no matter how long the board is, the work you do is mgh, turns out. It's independent of the length. All right? So what matters is the height of the truck, right? It only depends on the height. The work you do, the work you end up doing, and by the way, we're ignoring friction, okay? We're ignoring friction. The actual work you do is only a function of the height of the truck. Whether you directly lift it or you push it along an inclined plane, you do the same work. So why use a plane then, an inclined plane? Well, if you do that, the force that you have to push it with is less, because the force is equal to mg sine theta, and longer the plank, smaller the angle. Therefore, smaller sine theta, less force. Okay, with less force you can do the same work. So that's the thing about work. All right, less force doesn't mean less work. You just move it for a longer distance, but you do the same amount of work, which is equal to mgh in this case. So I said sine theta also appears in part B. That was the work done by gravity. Yeah, if you plug sine theta here, which is h over d, you get negative mgh. Okay, so whether you lift it directly or you push it along an inclined plane, doesn't matter for gravity. Gravity always does the same amount of work, which is equal to negative mgh. Remember, you are doing positive mgh, or you're doing a work equal to that number. And the same number, only negative, is the work done by gravity. So this positive and negative, you can think of it like an active and passive roles. Okay, so you have the active role, you're doing the work, you're sweating. Gravity is resisting you, it's passive. Okay, I mean, you can still do it. It's on the passive side, but still trying to oppose the motion in a way. That's why it is negative. All right. So as a general rule, the forces which opposes the motion will end up doing negative work. The positive work will be done by forces which are moving the object in that direction that you apply the force. All right. So if you're lifting an object upward, you are doing the positive work and gravity is doing the negative work. But if you bring it downward, okay, you do it slowly, gradually. I mean, you can still get tired while doing it. That's a different story. It has to do with the muscles here, and then you're, getting tired doesn't mean your work is going to be positive, okay? But when you're lowering the object, gravity is doing the positive work. Why? Because gravity vector points downward, or let me say weight, to be precise. Weight as a vector points downward, and displacement also points downward. If these two vectors are parallel, the work is positive. Cosine 0 is 1, right? So when you lower the object like this, you bring it down. Gravity is doing the positive work. You are on the passive side, okay? I mean, you're resisting it, but you're still letting it go downward. Because of that, the work you do is negative, okay? So by the work you do, I mean the work done by the normal force that is exerted by your hand on the object, which is upward. Normal force is upward, but the displacement is downward. Two vectors pointing in opposite directions, cosine 180, therefore negative 1. The work is negative, okay? So if you lower it from here to there, let's say 40 centimeters, whatever, that's your height, right? So the weight of the keyboard is mg, so mgh. Gravity does mgh, you do negative mgh. All right? So forces which are in the opposite direction do negative work. And you may say, okay, friction. We ignored friction here. You don't have to ignore it. You can include friction in your problems, but whenever the objects are in motion, the friction is always in the opposite direction of the motion. Therefore, you can say friction does negative work. That's okay. I mean, mathematically, there's no problem with it. But generally, it's better to say, better to explain this in terms of energy, which we haven't gone into yet, okay? So, I mean, you are familiar with the idea of energy in general, like heat is an energy, right? You do this, and your hands get warm, okay? You feel the energy. Heat is an energy, right? So why do we have heat? Because we have friction. If you just do this, there won't be any heat. So there has to be a friction. So friction has to do with energy. I mean, if you're feeling the heat, this means you're taking that heat from somewhere, okay? Heat always flows from one point to another. That's heat transfer or energy transfer. So it's better to explain friction in the context of energy or energy dissipation. That's the right word, okay? But it's okay, mathematically, you can say friction does negative work. That's not really wrong, especially in this class. That's perfectly fine, okay? But technically, it's better to call the change in the energy when friction happens. You call it an energy loss or energy dissipation, okay? You can never destroy energy. You can never create energy either. Energy can only be transformed from one form to another form, okay? We have potential energy, for instance. If you just hold an object, okay, you know that if you drop it, it may hit something and break it. So you give gravity some chance to do work, okay? So that type of energy, when we're just holding it, for instance, is called potential energy. It's similar to charging your phone, okay? You're storing energy in it. That's also potential energy, okay? And when an object moves, you know that when it hits something, it's gonna create some damage. You can throw a rock to the glass window, you may shatter it, right? So objects in motion, or car driving on highway, have also energy, which depends on the speed of the object, okay? So that you can call speed energy, or a better term is kinetic energy. Things in motion. So kinetic energy, potential energy, and we have energy in the form of heat. What about light? We get heat from light as well, or sunlight. There's sun radiation from sun. Okay, that's also energy. So energy has sound. How about sound? Right? Sound is also energy. You hear a car crash outside, you know, two cars collide. Heat is produced, maybe sometimes fire, but just the fact that you can hear it means that sound is generated, and that requires energy as well. So initially the cars were in motion, they had kinetic energy, and then when they hit each other, that energy, some of the energy is transformed into heat and sound. And some of the energy, initial energy, is used to deform the car's geometry, let's say, okay? I mean, the body of the car. That requires energy too. It takes energy to bend a wire or bend some metal, okay? So that's why it's very difficult to give an exact definition for energy. It's something you understand the more you think about it and more you solve problems, and we're gonna get in there, okay? So, but work is well defined. It just takes a force and displacement to work. Okay, so gravity may do negative or positive work depending on the direction of the motion, and friction always opposes you, and it's okay if you call it negative work, that's fine, but in general we think of it in terms of energy dissipation. Okay, so I mean, friction makes you lose energy. That's why you use WD-40, right? I mean, in moving objects, or maybe motor oil. You know, you want less friction to preserve energy. Okay, so that's the definition of work, and just an example. I think the idea is clear, and the unit is joule. And so let's see how this applies to objects in motion. Let's start there. Okay, so we have force. An object is moving. What do you expect? Okay, I mean, like in the first example I was showing you here, the simplest thing you can imagine. An horizontal force applied to an object sitting on the floor, and the object starts moving. Now, if there is no friction, F is the only force acting on it. I mean, there's of course mg and the normal force in the vertical direction, but in the horizontal direction, F is the only force. So F equals ma. You expect the object to accelerate, right? So if F is the only force in the horizontal direction, then according to Newton's second law, the object will accelerate. Now, if the object accelerates, and acceleration is constant, because F is constant, we can think about varying forces later. Let's say we don't change the force as we push it. We apply constant force. You expect a constant acceleration. And we know what happens when acceleration is constant. We have a set of formulas, remember? There are 4 formulas, at least 4, that you've been using by now. And one of them did not have any time in it, right? It went something like this. V final squared is equal to V initial squared plus 2 times acceleration times delta x. I think that was the formula, right? And you can put an x here. That's how the book shows it. This was the formula, equation number 4, if you will. Now in this case, d is what we mean by delta x, obviously. All right. And V initial and V final could be anything, okay? I mean, you can start from rest, and the V initial will be 0 or not. It doesn't matter. Maybe the object was already in motion, and then you start pushing it. So Vi is non-zero, but the Vf will be greater, okay? So let's use this then. Let's use this equation, and let's solve for A here. I'm sorry, let's do this. Let's rewrite it by plugging, instead of A, let's just plug in F over M. Okay, so we will have Fx. I'm just going to write Vf now, because it's in the x direction. We know it's one-dimensional motion. This is the x direction. So Vf squared is equal to Vi, initial velocity squared, plus 2. Instead of A, I'm going to write F divided by M. That's Newton's second law. Times delta x. Well, delta x is d. Okay, so what happened here? We got rid of acceleration. That's what we did. We're using the kinematics formula without the acceleration. Instead, we have the force now. But see, F times d. We have F times d here. F times d is work, right? This is work. Or work done. Work done. Work done by F when the object travels a distance d. So let's solve this equation for work then. Okay, so you can subtract Vi squared from both sides, and you will have here 2 times W, that's work, divided by M. And if you solve it for W, work done will be, okay, multiply by M, divide by 2. Divide by 2 means 1/2. So 1/2 multiplied by M, what? Vf squared. do the same thing for the second term, minus 1/2 m VI squared. Okay, so we solved for work. But in this expression, there is no force, there is no acceleration. What do we have? We only have mass and velocities, initial and final velocities. That's a very good formula, very important formula. We don't need to know force, but we don't need to know really what happens between, or we don't care, or it's not in the formula, between the initial and final states, right? All we need is the initial velocity and the final velocity. If we know these two, we know what work has been done on the object, right? So this is a quantity only depends on the initial and final values. And the thing that we're subtracting here, which is 1/2 mvi squared, looks similar to 1/2 mvf squared. I becomes f, okay? So why don't we call this quantity 1/2 mv squared? Why don't we give it a name, okay? Call it k. Just one letter is better than 2 or 3 letters, right? Just call it k. So w will be equal to k f minus ki, because we use it for the final and the initial values. Okay, in other words, delta. Remember, delta in physics means difference. It's final minus initial, delta k. Okay, so it's simplified. Now it's just one equation, w equals delta k. Okay, so this k that we defined as this is called the kinetic energy. Kinetic energy, sometimes called Ke. It doesn't matter what you call it. The book calls it. The book calls it K as well. All right. And it's called actually the work energy theorem for that reason. You have work on the left hand side, energy on the right hand side. Work energy theorem. It's a formula. That's what it is. Okay. Very practically useful. Even if you don't know the force, you can find the work. Think about that, okay? That's why it is good. And you don't know how far the object moves either. The definition of work is force times distance, but without knowing those two, just by knowing the mass and the kinematics of it, initial and final velocities, okay, you can find how much work is done on the object. But, okay, there's an important factor here. When we derive this formula, remember, we used a very simple case, the original problem of pushing an object horizontal, okay? Now, what would happen if we had other forces, friction present, or maybe 3 people pushing it at the same time at different angles, okay? Then this W here is the work done by which force? Friction? Your friend? You? No? I mean, which force? Because there's only one delta K for the object, but there are many forces present. There could be in general, okay? And there are, and practically there are many forces acting on one object. So which one are we going to pick? You may be asking yourself, and that's a very good question. So we call this then, this has to be the total work. Total work means you just add them up, okay? Remember, work is a scalar quantity. It's not a vector. It's just a number. You can add them up, but make sure to keep the sign, positives and negatives, okay? They have to be exactly the way they are. So, like in the previous case, we had the work done by the force that we're pushing, and then there may be friction. I'm going to call it little f or FR for friction. Work done by gravity, and then work done by your friend, and then his friend, blah, blah, blah. Okay? I mean, you may add as many as you want, but add them up. Add everything up, and that will be the total work. That total work is the work in the work-energy theorem. Okay, this is the work-energy theorem. The work done on an object, the total work done on an object is equal to the change in its kinetic energy. Check the dimension of kinetic energy again. Dimensional analysis. We have mass. 1/2 doesn't matter. 1/2 is just a number, dimensionless number. But m is mass. V is what? Length over time, or distance over time, squared. So we get the joules again, right? Remember, we had the dimensional analysis here. ml squared over t squared. Same thing. So the dimension of both sides are equal. It has to be, otherwise it would be wrong, right? Every physics equation should have the same dimensions on right and left hand sides. Also, if you're adding or subtracting two quantities, they should have the same dimension. Okay, remember from chapter 1, dimensional analysis. So it's joules, okay? So kinetic energy is measured in terms of joules, just like work. And the dimension is ml squared over t squared. Okay, so that's the work energy theorem. Now let's find how much. Let's solve a problem from the book. Let's solve a problem from the book. Instead of trying to come up with problems, let's use a problem from the book. Let's see. Work energy or kinetic energy. Okay, so it has to be number 20. Let's do number 20. A ball of mass 0.1 kilogram moving with speed 2 meters per second hits a wall and bounces back with speed of 1 meters per second in the opposite direction. So the speed is halved. Okay? What is the change in the ball's kinetic energy? Okay, this is not about work, it's just about the change in the kinetic energy. But there's a good point here. First, the ball is moving to the right, let's say, 2 meters per second, and it's 0.1 kilograms. Here's the ball. And 1 second later, now you see the ball moving in the opposite direction. 1 meters per second is its speed, okay? Speed changed, velocity changed because of the change in the magnitude and direction, okay? But the change in the direction has nothing to do with the change in the kinetic energy. Okay, the change in the direction has nothing to do with the change in the kinetic energy. The change in the kinetic energy, delta K, is because of the change in the magnitude. Okay, it goes from 2 to 1. That's what I'm talking about. That's the magnitude. Why? Because it's 1/2 mv squared. That's why. Okay, this v squared here. Remember, v as a velocity, as a direction, but if you consider the magnitude of it by simply putting bars or simply dropping the arrow, now you're talking about the magnitude. The information about the direction is lost, okay? And then you square it. By the way, in terms of the dot product I was telling you earlier, you can also write it like this. The dot product of v by itself is v squared, so take the square root of that and you get v. Okay, just something to keep in mind, the dot product. In any case, it's a scalar, okay? No direction. So, if the ball bounced with the same speed, 2 meters per second, there wouldn't be any change in the kinetic energy, okay? That's the thing about problems in this chapter. Think about how the angles were important when you were solving projectile motion problems. The initial angle, final angle, etc., right? They were important, the components. But when you solve problems using energy methods, you don't worry about the direction anymore. Okay, so don't worry about the angle in general. There may be some cases where, you know, you're looking for some angle. It depends on the problem. And in general, the direction doesn't play a role in the kinetic energy. Okay, it's v squared. Therefore, don't worry about direction. In a way, it is easier. Okay, energy methods is like an alternative method to solve problems without worrying much about directions and angles, therefore sines and cosines. Okay, that's the thing about this chapter. So delta K only depends on the change in the magnitude. Okay, so I think that much is enough. You know what I'm talking about. So 1/2 mv final squared minus, and if you may say, okay, why is it not 1/2 mvi squared minus 1/2 mvf squared? Okay, I mean, who says that the change in the kinetic energy has to be final minus initial? Well, yeah, I mean, that's a legitimate question. It's just a convention, okay? There may be a book somewhere where they have the opposite convention, but I'm sure they mention it in the book, okay? So it's not physics really, it's just convention. You just accept it, okay? So in this case, delta K will be a negative number. It'll be a negative number because the object is has slowed, okay? So you have here 1/2 m. Why don't we factor this 1/2 m? 1/2 m. M is 0.1 kilograms. So final velocity is 1 meters per second squared minus 2 meters per second squared, okay? So this many joules, but this is obviously a negative number. The change in the kinetic energy is negative. Maybe now it's not in a problem, but we can still think about this negative sign, what it means really, okay? And to do that, think about that work energy theorem, okay? I mean, work will be negative also. Work energy theorem says the change in the kinetic energy is equal to the work done, the total work done on the object. And we're ignoring gravity here, actually. I mean, gravity, of course, pulls the object downward. We're talking about actually a path like this, and then when it bounces, it's going to go like this. Okay, I mean, we can think about gravity too, but for now, let's just focus on what happens in the horizontal direction. There's a negative work, okay? So that work is done by the forces, the interaction forces or the contact forces between the ball and the wall during a very short time interval. In that time interval, if you could film this and watch it in slow motion, you would see the ball squeezed and then expand again during the interaction, okay? So while that's happening, there are some internal forces within the ball that deforms the shape, but also obviously the wall has to exert a force to the left. I mean, that's pretty obvious, right? The wall is there. It stops or bounces the ball. There must be a force to the left. That's about it. I mean, that's why we have a change in the kinetic energy and a work. So the work done by the wall is that, okay? But that's not part of the problem, so don't worry about it. But let's find a problem where they do ask the work. So 23. So this was 22. Let's do 23. Jim rides his skateboard down a ramp that is in the shape of a quarter circle with radius of 5 meters. Okay, I need to draw this. So a quarter circle. Okay, a full circle will be like that. Oops, very bad drawing. Something like that. Okay, with radius of 5 meters. This is also R, of course. It's a skateboard down a ramp, so maybe the beginning of the ramp is something like this, doesn't matter. But here's the skateboard, and Jim is right there. At the bottom of the ramp, okay, so maybe it goes on like this. This is how the thing goes. Jim is moving at 9 meters per second. So by the time he reaches here, the skateboard is moving 9 meters per, moving at 9 meters per second. Okay, so Jim and his skateboard have a mass of 65 kilograms. Now, that is the final velocity. Okay. How much work is done by friction? Okay, work done by friction, in other words, energy dissipated due to friction, as the skateboard goes down the ramp. Now, I guess we're supposed to assume that he starts at rest here. So the initial is 0. But of course here, Jim has a speed, a circular motion, right? A speed something between 0 and 9, obviously. Alright, so how much work is done by friction as the skateboard goes down the ramp? Now, what are the forces acting on Jim and the skateboard? I can think of 3. Actually, just 2. I'm sorry. I can think of 2. No, 3. 3, of course, 3. There's mg, weight. There's friction. Now, my drawing is really bad, but imagine a line that joins this mass to the center here. The friction will be perpendicular to that. So the friction changes direction with the velocity. Okay, by definition, a kinetic friction force is going to be always anti-parallel to the velocity vector. So you expect the friction to be here, little f. But mg is always downward. And the third force, the normal force, is this way. So normal force and the friction are always perpendicular. And mg is always downward. Now remember, the forces which are perpendicular to motion never do any work. Okay, so the normal force is not doing any work here. Friction is doing work, that's what we're supposed to find. What else is doing work? mg. Okay, mg, does mg change? No, mass is conserved, g is the same within 5 meters. See, r is 5 meters, therefore this distance is also 5 meters here. Now remember the truck and the refrigerator problem, okay? It didn't matter how long the platform was, or the plank, the wood, whatever surface you used. The work done by gravity was always negative mgh when you were lifting the object. In this case, it's not a straight curve, it's not an inclined plane, but the same principle can be applied. The direction or the length doesn't matter. What matters is actually the vertical displacement. Okay, that 5 meters, that's what matters. Okay, so if you want another reasoning or a different way of seeing it, you can always take a curve, and not necessarily a quarter, but any curve. Okay, you can take any curve, and you can start with little, very tiny increments, like a stair. You can go horizontal. If you go too far, you can go downward. If you're too far meaning if you move too much away from the actual red line, you go back to it by switching to horizontal. Vertical, horizontal, vertical, horizontal, vertical, horizontal, vertical, horizontal, vertical, horizontal. Okay? You go like this. And actually, the smaller the steps, the better the approximation, right? But think about it. When you're doing that, every time you move horizontally, gravity is doing zero work. But every time you're going downward, gravity is doing a work equal to mg times this distance here, vertical increment. And then you have other vertical increments. You add them up. In the end, you end up with a total height. Total height times mg will be the work done by gravity. Okay, so whether it's a quarter circle or it's an elliptic curve, doesn't matter. What matters is the total displacement, which is downward. So the work done by gravity for this problem then is not negative, positive, because your motion is downward. If you're unloading from your truck, gravity will be doing positive work, right? Same thing here. So the work done by gravity will be simply mgr. R means the height. mgr. Work done by normal force is 0. And of course, work done by friction, that's what we are trying to find, WF. How do we find it? We know that if we add these up, on the left-hand side, we will have the total work. On the right-hand side, the total work will be mgr. Okay, so the total work is equal to work of friction plus work of gravity, work done by gravity. Okay, so you add the left hand side, no work done by normal force, work done by gravity plus work done by friction is equal to total work. So mgr plus work done by friction. That's a question mark here. I just added the right and left sides. Okay, so mgr plus work done by gravity, work done by friction, is equal to the change in the kinetic energy, which is 1/2. Okay, let me move it a little bit here. 1/2 mv final squared minus 1/2 m v initial squared. Now the skate starts from rest, so this is 0. It's only 1/2 mvf squared. Okay, so solving this equation for the friction force, we have 1/2 mv final squared minus mgr. Okay, will this be a negative or a positive number? Friction, remember, friction always opposes the motion, so you expect this to be a negative number. Is it so? Let's check. So 1/2 times mass, what was it? 95 kilograms, and it was, I think, 9 meters per second, the final speed. 9 meters per second square. Okay, don't forget the square. It's a very common mistake. Happens all the time. Don't forget the square. 9 squared minus mgr, so 95 kilograms. G is of course 9.8 meters per second square, and R is 5. R is 5 meters. All right, So let's find this. Times 95 times 81, that's not 81, that's 9 squared, minus 95 times 9.8 times 5, negative 807.5. joules. Okay, that's the energy dissipated. So what happens to this energy? It becomes heat mostly, and sound. I'm just going to check the answer. Chapter 6, problem 23. Chapter 623, negative 550 joules. Okay. Well, we got the negative right at least. 65 kilogram, not 95. Sorry, 65. I copied the number wrong. Okay. So if mass is 65, then this is, according to the book, negative 550. Let's see if this is correct. So let me go back to that. 0.5 times 65 times 81 minus 65 times 9.8 times 5, negative 552.5, or approximately, as the book, okay, joules. Okay, so it said 65, but I read it as 95. That was the issue. Okay, so that's a very good problem where you apply both concepts of work energy theorem and the negative work done by friction or energy dissipation, you know. And we talked about the independence of work done by gravity, independence of it from the path. Okay, a quarter circle here helped us to find the height basically, but in general I could say, hey, this is the skateboard path, something like this, instead of a quarter circle. Okay, now you may say, hey, hang on a second, okay, by stretching this path like this, you're increasing the distance, so he still goes down 9 or 5 meters, but there's more interaction with the track, so friction would do more force. Okay, you may say things like this. The distance may change, but the actual friction force also changes, right? The friction force does change because friction force, kinetic friction, is equal to mu k times normal force. And by changing the shape of the track, you're also changing the value of the normal force. So that's fine, okay? What I'm saying is, no matter what shape it is, in the end, it just depends on the change in the kinetic energy. So the problem could be given you in this form. The answer will be the same, okay? We're not finding the friction force, we're finding the work done by the friction force, okay? So different path would give you different friction force, but not different work done by friction or different energy dissipation by friction. All right, okay, so that's much about work energy theorem is enough. Let's talk about potential energy now, okay? Potential energy. By the way, we also talked about the normal force not doing any work in this problem, okay? And that is actually true for circular motion. I think the best example would be a satellite around the Earth. When the satellite is in motion, the force is gravity. That's the only force. And that force is not doing any work. Force of gravity is not doing any work on the satellite, which is going in a circle around the sun, around the Earth. If no work is done, no change in the kinetic energy either. So the satellite is not speeding up or slowing down, right? Remember, that can only happen if you change the orbit. If you move to a different orbit, speed will change. But that's when you have to do work against gravity, or the work will be done by gravity if you're getting closer to the Earth, right? So those are exceptions, but as long as you remain in a circle, you do not expect the rotation rate, revolution rate, or the speed to change, right? No change in the kinetic energy. Now, is it always the case? No. What if you have an orbit other than a circle? An elliptical orbit, which is more realistic, right? Even Earth, when it goes around the sun, it's not a perfect circle, it's different. And due to that, especially if it's a comet around the sun, it's a very elongated, if you will, ellipse, okay? So what happens is the kinetic energy changes throughout the year, let's say, okay? So velocity changes, but overall, 1 year remains 1 year, okay? So the math is a little bit different in that case, but the main ideas are there, okay? So in circular motion, let's go back to circular motion, forget about ellipses. The forces, the centripetal force doesn't do work, okay? When you connect a string to a piece of an object and then you swing it, okay, a circular motion that has a string here and then an object. So we're talking about the tension force here when you're holding it. This tension force will always be perpendicular to the velocity in principle, and it will not do work. But you may say, hang on, I mean, if I do it for an hour, I'm going to get tired, okay? I must be doing some work. Actually, you are. If you analyze it carefully, when you're swinging it like this, remember, your hand is also making a circle here. Your hand is making a circle, and the object attached to the string is making a larger circle. And if you draw an accurate picture of it, you will see that the angle is not 90 degrees. Okay, so this is the circle your finger is making in air, and this is the larger circle of the rope or the object. So when the object is here and your finger is here and the string is like this, okay, if you think about it, the velocity vector is still perpendicular to the center of the larger circle, that is still 90 degrees, but the angle between the tension vector and the velocity vector, this angle is less than 90, which means the tension vector will have a component along the velocity. Okay? If that happens, there's work. There is work. And are you doing this horizontally or are you doing it vertically? If you're doing this vertically, other things change as well, because gravity is acting downward and the velocity will not be a constant to begin with. Okay, so there are complications there too. And the tension will change, of course. Tension will change. So since I mentioned the changing forces, before we do potential energy, let's talk about work done by changing forces. Okay? Now, changing means you can change things in time. You can change things as you go along, okay? So if the problem was pushing an object horizontally, even in that case, the force may not be a constant. So you push or pull, doesn't matter, the object here. So it goes from A to B. But along the way, I mean, this is a displacement vector, D, but along the way, F may not be a constant. Okay, I mean, even if you're the only person who's pushing it, you may not be able to push with an exact force every second, right? But we're talking about the force that depends on distance, okay? Not time, but distance. You can plot it. If you wish, I can just plot it right below it. Maybe it's going to be better. Let this be the distance. Let this represent the force, okay? So you may push with the force and then maybe get tired later. You can still get the job done, or you may increase the force, and then by the time you reach point B, maybe the force is more than what you started with. Why not? Okay, it could be anything, right? It could be anything. So what is work? Is it equal to F times D? It's not. It's not. How do we know it's not? Well, if it were, what is FD? This is D. This is x equals D here. This is x equals 0, your origin. So this distance is D. Now F times D means the area here of a rectangle. Okay, so this F. So if this F here is what you started with, let's say, imagine the area here of this shaded area, shaded region. That is FD. Okay? So if we're considering areas, why don't we look at the area below the actual F? Okay? Because we know that if the force was a constant, that area, the shaded area, would be work. F times D, no question about it. For constant forces, F times D is that. But if the force is changing, and we can't use that formula anymore, can we use something like that? Meaning, can we use this idea of areas to find work? Okay? So, let me replicate that here. So, your function, again, we're talking about F as a function of distance, not as a function of time. Okay? There will be a place where we actually consider changes with respect to time as well. But for the time being, we're looking at force as a function of x. Okay, F is a function of x, f of x, whatever function you have. Okay, I just drew some arbitrary. But the point is, can we use this idea of rectangular areas to find the actual work for this problem? Okay. If the force was constant, we know the area FD is work. Then what we do is look at very short increments in x. For instance, I mean, this is easy here. Let's start right. If you go from here to there, a very short interval of delta x. Now, according to this particular shape here, you can say F doesn't change that much, right? So this area here is still work. F times delta x. But then if you look at the change from here to there, you have a problem now. That's still some delta x, okay? I mean, these could be equal intervals, very small or different, doesn't matter. The idea is important here. But then if it's going to be a rectangle, which rectangle are we talking about? Like you can use the larger value or smaller value. If you use smaller value, this is the rectangle. If you use the larger, I don't know what color, let's use blue, then you would have this one. You see what we have here? So you're either actually finding a work related to that delta x, the blue one actually, which is going to be more than you want, or you want the green one, which is less than you want. The truth is somewhere in between. So the solution is actually to consider a shorter delta x, because the shorter you get, those two lines get close to each other. Okay, this is the very basic method of calculus. Okay, Isaac Newton and Leibniz. We know that we're told that they found calculus together. Some people say it's Leibniz and Newton copied. Some people say no, they simultaneously came up with the same idea, and I don't find it, illogical. I mean, it's possible because it's same kind of tools that he used. But what they did is this: they thought about very small increments. Okay, I think Newton said, let's use really tiny rectangles, and I think Leibniz said let's use lines instead of rectangles, but these are very tightly spaced, so it comes down to the same thing. Okay, this is the mathematics of infinitesimal increments. All right, but what you do is you add them up. So you think about all these rectangles, very tiny rectangles, much tinier than I just drew, but you add them up. So what you end up with is the total area under the curve. Okay, now when I'm shading this, I'm careful not to go above that actual function. Okay, so the area under the curve, that is work done. Work is equal to area. Okay, that's the important result. Now that applies to me pushing the fridge with a varying force, but what about friction? Now we are told that friction will do a negative force, a negative work, because it's pointing in the opposite direction. And it's not only true for friction, but any force that acts in the opposite direction of motion, right? And those forces may vary too, okay? I mean, so it's quite possible that you may end up with a some force or net force, let's say, that looks like this, all right? So what are you going to do then? You can still find the areas, but just divide it into two areas, two sections, A1 and A2, let's say. This is the force distance graph, X. Whenever you have an area below the F equals 0 line, these will be negative, and these will be positive. Okay, so when you're adding them up, you take that into account. You subtract some of the areas from the others. Okay, so that's all. I mean, for varying forces, that's in your book. I don't know what section that is right now. Maybe later in the section. So yeah, they did it. Section 6.6, work done by variable forces, and they used the exact analogy I did here with the small displacement idea. A very good example of varying forces are springs. Springs. Okay, I'm talking about wires that are curled around a cylindrical core, and you take them out. An ideal spring in physics is the one that you can stretch and compress. And the force you have to do that is proportional to the amount you compress or stretch it. And it is linear in that compression or stretch. So if the initial length is this, and then you stretch it to that length, that can only be done by pulling it to the right, like this, F. Imagine the left-hand side is connected to a stable wall or something, okay? So it was L, now it is L prime, okay? It elongated, but the change in the length, L prime minus L, that is this. Call it X, for instance, okay? I'm saying this force is proportional to X. This means proportional. Proportional to X, not X squared or anything like that. For ideal springs, okay? Actually, to be exact, we have to include a negative sign. This is called Hooke's formula, by the way. So let's try to be precise. Let's put an x-axis here. Okay, and I'm going to call this point here x equals 0, my origin. All right, so when I'm stretching, this end of the spring is a positive number here. But when I'm compressing the spring, let's say here, compression, if I do that, this point is still the 0 point, but I'm on the left of 0. So my x is a negative number, and I'm actually pushing it to the left because I'm compressing the spring, okay? Now, the formula that will give me force has to work for both cases. That's why I need a negative sign, okay? So here's how it works. According to Newton's third law, action-reaction pairs, remember, I exert a force on the spring. In return, the spring exerts a force on my hand, right? So that force, let me use color blue, will be in the opposite direction here. Fs, how about that? S stands for spring or restoring or elastic, whatever you want to call. And when I'm compressing the spring, I'm pushing it to the left in this picture, but the spring pushes my hand to the right, according to Newton's third law. So Fs is to the right. So when x is a positive number, Fs is a negative number, right? And whenever x is a negative number, Fs is positive. Okay, so this proportionality only tells me that it's linear in x. Okay. Of course, when x is 0, there is no force. X is measured in newtons. F is measured in x is measured in meters, F is measured in newtons. They're not the same. Remember, every physics equation has to have dimensional equivalence, or they have to be dimensionally consistent. And also, we know that some springs are light, some springs are strong. Imagine the ones under your car, or imagine the ones in your mechanical pencil. They're not the same, right? So I need something that describes how thick that wire is, how strong it's made of, okay? So all of that and the dimension issue is embedded in a constant, okay? So that's what makes a proportionality and equality, or equal, by putting a constant here, K, a spring constant. But I'm not finished. I have to take into account that when x is positive, F will be negative by putting a negative here. So if x is negative, two negatives make positive. So Fs will be positive also, okay? So this is the formula for a spring called Hooke's law. Hooke's law. All right? That is the restoring force in a spring. Not the force you exert on a spring, but the spring exerts on you. Or if you think about it, just like whenever you have a cable stretched, the tension inside that cable is everywhere the same if it's a uniform cable. Same thing applies to the springs. If you consider a point somewhere along the spring, let's say here, at that point, the material in the spring has to carry that tension in a way, okay? So we're talking about the tension force in a spring in a way, if you will. Okay, that's the analogy there. That's the restoring force, equal to negative kx. The only thing is, if it's not stretched or compressed, F is 0, and that makes sense. Okay. So if you're given a problem in an exam or whatever, okay, and if you're given L instead of X, please do not just multiply the spring constant by L to get a force. No, L is the unstretched length. That has nothing to do with the force. The force only comes from X. And X, or delta X if you will, if you want to think it like that, because I started from 0. What if you started from 5? Then X minus 5 is delta X. That goes into the formula. Okay? So that's Hooke's law. The force in the spring is proportional to the change in the length of the spring, and that negative sign guarantees that the force will always try to restore the spring to its original unstretched or uncompressed position. Okay, but in real life the spring may not be ideal, meaning you stretch and stretch and stretch. After a point, it doesn't go back anymore because you basically destroyed the spring, okay? Or you may have other terms, I don't know, x squared, x to the cube, depending on the material, right? So let me plot this force, and I'm going to stop there and then maybe make another video about the potential energy. So if I'm plotting for this specific spring attached to the wall thing, so let's plot two things. Let's plot the force I exert on the spring, and let's plot the force, restoring force in the spring. The force I exert as a function of x, and the force in the spring as a function of x. So this F is equal to not kx, not negative kx, but just kx, and this is negative kx. So negative kx will be something like this. It goes from 0. And the positive kx is obviously like that. Okay? So if you think about it, why did I bring this up? We were trying to find the work done by forces that vary along the x direction. So now we may need to consider the area of a triangle here if I'm stretching the spring. If I'm stretching the spring, the force I exert is in the same direction as the displacement of my hand. So the work I do is positive. I'm active. Spring is on the passive side. It just goes along with what I'm doing. Okay? So the work I do has to be positive. Positive work done by me. But what happens to the spring? See, it's an area under that line. All right, so the spring is doing negative work. Think about this. Let's say the spring is already compressed. I'm holding it there. Okay, I'm holding a spring which is compressed, and I'm releasing the pressure gradually. What will happen? The spring will expand as my hand moves close to the equilibrium position. X equals 0 is equilibrium position, which means the spring is doing the positive work now. Okay, here spring pushes. Here I stretch the spring. Here I stretch the spring. So when I'm stretching the spring is doing negative work. But when I'm releasing the pressure, so my hand is moved by the spring, then spring is doing positive work. Okay? And I'm doing negative work when that happens. All right, so I'm going to stop here, take a break, and then come back with potential energy. All right, Alt.